Well, higher order rocks, of course. And so the idea with higher order rocks was that these things would fall, and if they hit a hard surface, they release the lambda, yet more lambdas to collect. So that was roughly the challenge. Now, the challenge was actually sort of done in stages. It started off with a relatively simple specification, which was extended over the course of 3 days, within which we had to submit something. There was a lightning round which lasted 24 hours, and as well they changed the spec halfway through just to keep us on our toes. But this talk is about our solution to this, and we used Haskell to implement a little AI that navigated around. And I suppose the reason I wanted to give this talk is to give you a feeling for how people program under lots of pressure and hardly any sleep, and you really want to win this competition. So it's sort of, well, it was a fun weekend, but it made us sweat. So how did we go mining lambdas? Well, of course, we had to send boards to help us, and they'll make an appearance later on. But the basic structure that we used to navigate these mines was an infinite game tree, so a little bit like this one. So each of these ends represents a mine state, so that's basically the state of the world. That includes where the lambdas are, where the robot is, how many lambdas you've collected, how many moves you've taken, etc. And these edges represent moves that the robot could take from a particular point in the mine. So in this simple example, we just have 3 moves left, down, and right. Of course, the robot could do more than that in the competition, but to make it fit on the slide, we have a tree like this. And the idea was that we would sort of navigate around this tree looking for the optimal mine, the optimal position in the mine that would give the best score, and that would be sort of the path to that mine, be the output of our algorithm. So the basic building blocks of this tree were relatively simple. We started off with these things called tiles at the top, where a tile is basically one of those squares that we saw in the first slide. It's either a robot, a wall, a rock with a Boolean parameter, which that parameter told you whether the rock was falling or not. Only falling rocks were dangerous according to the spec. We won't go into the details. Or you had, of course, lambdas, bits of earth which you could dig up, empty squares, and the exit itself, which was opened when you had all the lambdas. And so we had this thing called a layout, which is basically an array from coordinates to tiles, because we wanted to have quick access to see what was particular coordinates we wanted to inspect it. And we bundled this up in a particular data structure called the mine, which had a layout. It had the robot as a particular coordinate, even though you could look it up as well, just for efficiency. The number of lambdas in the current mine, again, you could look that up, and the number of moves taken to get to this particular state. And so moves consisted of going left, going right, going down, going up, waiting, which meant just staying still, and aborting, which meant saying, I've had enough, just give me all the lambdas that I've got, and stop right now. And the idea really was to go from one node to the next node using something called the step function. And the step function was nothing more than something that took a mine, took a move, and produced the exact sort of final outcome back. So it's a pure function. This is all the input that was required for the first version. And what we tried to do was encapsulate each mine state as a single pure value, which meant that we could garbage collect things behind us in the tree as we were moving through the structure. So why trees? Well, one reason for this is laziness was very useful in this. It allowed our trees to be infinite, so we could capture the entire state of the puzzle as a single value, which we were lazily evaluating. So this tree is possibly infinite because you could move around the mine forever. But of course, because it's lazy, we can represent this as a single value and just lazily evaluate what we need to know as we go. Another point to note about this tree, of course, it's a pure value. It's a Haskell, of course, which means that the values, the nodes are all what I call stable. You know that the value at a particular line will always be the same, no matter how you traverse the tree to get there, no matter which other traversals or strategies you've taken to uncover this particular node. And we'll see how that became useful later on. So the actual tree structure that we used was a trie, slightly modified trie. So a trie, in case you don't know, is this data structure here. It takes a K and a V, so K is for the keys, V is for the values held the trie. And at a particular trie node is V, which is basically the value that's the payload of the trie at this point, followed by a mapping between the keys and possible other tries. And I find a useful way to understand these tries is basically as a kind of map. It's a map between not just K's and V's, but lists of K's and particular V's. And so you can see that in this lookup function. So lookup says, okay, we'll take a list of keys K, we'll take our try, K to V, and produce maybe a V. So if we look up the empty list, that means that we've hit the right node, this is where the ditch is to be found, and we return just the V that we want. Otherwise, in the second line, we have the third line, we look up this K, and we do an ordinary map lookup in the KVs, which is basically where we hold the mapping between the keys and values. If there's nothing, then we bail, and if we get back a new tree, then we look up the rest of the Ks and stuff like that. So we really are descending through the tree. So in case that's not clear, we start off with our mine M0 there, which is the tree or try 0 rooted at the M0. If you want to go down, you follow that down link, you get the tree rooted at M2, then you follow the L, you get the tree rooted at M7, and because you're looking at nothing, M7 is the value that you're looking for. Okay, so far so good, it's very straightforward. And of course the reason we were looking at these try structures at all is because we're interested in traversing them. We're looking for a solution, we're looking for the optimal line. And so we were doing initially a breadth-first search, which is defined like this. So breadth of T is something which gives you a breadth-first enumeration of all the values, so all the lines in this case. And so the stems function is basically something which takes a list of tries that you're considering and extends it to with the tries that, there's a typing error there, stems should be, but effectively, you take your try, you unpack it, so you take this V value, with my shadow, no, too short. Okay, well that V there, and you append that to the front of the recursive call to stems on T's prime, where T's prime is the list of trees that you have, and you append onto the end of that all of the children of the current term that you've got. So recursively, that should be fairly clear that that's a breadth-first traversal. The breadth-first search then simply takes some predicate P, and you will filter out all the values that satisfy that. You will keep all the values that satisfy that predicate P. So I've lied to you a little bit in this explanation because we weren't really interested in these V's. We weren't interested in mines per se. We were interested in the paths to the mines. How did we get to that mine? That's what we really wanted to do. And furthermore, we didn't want to just sort of say, this is a good path and that's the end of the solution. We wanted to say, this is a good path. And if you wanted to resume at this point, here's the rest of the trees that you can carry on traversing down the tree from that particular point. So what we're going to do is going to modify the breadth first, or the breadth function at the top there, we want to modify that V, which means that in turn we can modify all these different paths. And it's really very simple. We sort of just did this. Ugh. Okay, it's not as bad as it looks. Basically, we're just doing a replacement so we're not just giving you back these, precisely giving you these K-tree things, which are the paths to a particular node, this K's, and the try that's associated to that path. Well, the reason we've opted for this, again, we'll become clear in a minute. One thing that we had to consider as well was perhaps pruning values of the tree. So, if, for example, our robot traversed left and then right, or right and then left, it's possible that actually the mind state that he ended up in was the same one. Right? So this M6 and M10 values, it could have been the same mind. And so we needed a strategy for removing those things to stop the duplication of exponentially growing trees in every direction. And so in order to do that, we had some modified version of the stems function, which we saw earlier on. And just to highlight the changes that were required, we opted for a hash map way of doing it, or a hashing strategy for this, because it was very expensive to compare two mines, because that involved traversal of the entire array. And so we thought, well, let's just hash these things and just compare them to hash values. So we had this set called the visited set, and the basic idea was when you traversed some new part of the tree, you would check to see whether or not you visited that place before. If you had not, or if you had, then it would return nothing, which would say, yeah, you've already visited this place, too bad. And you would ignore that node, continue traversing with the visited set unchanged, and the tail SKTs on the other side. Otherwise, if you just had a new visited prime, that means you visited some new nodes, then you would basically use that new visited prime set in the rest of the traversal to go through and sort of prune out the values as you had to do your traversal. There were other things that we did to improve efficiency. We used queues rather than lists because of the expensive concat operator. Yeah, this pen was expensive because, of course, you're continually appending lists, so queues were better. And indeed, priority queues were even better because that gave us a very simple way of implementing the A-star algorithm. The A-star algorithm is a well-known searching heuristic or pathfinding heuristic in the AI community. And priority queues are basically the only tweak you need to this data structure to get that. Details are in the paper. Okay, we've got the point where we've managed to traverse this tree, or it's have a strategy for traversing it. But what strategies do we use? Where do we go? How do we traverse this tree? Who do we turn to for good mining strategies? Well, we have the 7 dwarves, of course. And so the idea was to have these strategies encoded at a higher level, as higher order functions that you could put in some comparison functions into to get up the value. So what we have is this type strategy here, which takes the game tree and gives you back a path and a particular score associated to that tree. And then as an example of a very naive strategy, we have this exhaustive one, which basically says, do a breadth first search after you've got the mine, and you check to see whether the robot is done. So has he traversed the entire, has he managed to get all the lambdas and exits, and you map second one gets score, basically just to get things into the right format. But effectively, this would have worked if you had a very powerful computer and a lot of spare time on your hands. But that's not quite what we wanted. We wanted something more optimal, or at least not optimal. But anyway, so one strategy that we went for was this comparison idea, where we say, okay, we're trying to go from one lambda to the next lambda, and the idea is we order our lambdas according to some ordering, and we traverse the map, getting these lambdas one by one, and if there are no more lambdas, then we bail. So this comparison basically takes into account comp, which takes into account the coordinates of the lambda that you're looking at, takes into account the path that you've got remaining in the game tree, quite a lot of stuff. And then if there are no more lambdas, then you look for the exit, and if you can't find the exit, you abort. But if you can find the exit, then you go through. Otherwise, you call this path to lambda, which basically gives you all the lambdas that you might want to go and get, and you add the paths to lambdas, and you follow those paths through. So I'm sort of omitting a few details here, but roughly speaking, that's the idea that we were aiming for. And of course, we had different strategies. Each dwarves had different strategies, and of course, there were 7 dwarves, so we had to encode at least 7 strategies. So Doki was the one that went for the first lambda that it could find. Sleepy was the nearest lambda. Grumpy, Smoke was the lowest lambdas, low was Grumpy, and Happy went for the highest lambdas he could find. Bashful went for clustered lambdas, which is sure I chose that. Sneezy sort of did an exhaustive search, but the idea was that he would jump around at different values and do a search and jump and do more sort of a final search, but we didn't have time for that really. And Doc did an A-star nearest path algorithm using the thing that I described earlier on. So we had all of these strategies to choose from. But who is the fairest of them all? Which one do we deploy to our mines? That's the real question, right? How do we do that? Well, the answer, of course, we deploy them all, right? So the notion that we had here was you have these things called n bars. We have a value which holds the best known solution so far. And we update that best known solution as we go through, and ask all of the dwarves to do it all at the same time, and concurrently we'll update this value if they have found something that's better. So improve is something that takes this n bar, which we're going to try and prove. It takes a list of paths and scores. So the A there is the answer, which is the path, and that's the score. And you would do first a deep seek on the X, which is the score that you've got. The reason for that is that you want your dwarf to first have fully evaluated his path and score before checking to see whether or not he's found something better than the cell. Because when you access this n bar, it's a locking sort of semaphore type operation. You'd be locking everybody up while you calculate your tree lazily. That would be limited. So you first calculate that. You check your n bar. If it's better, you swap. So the actual, nitty-gritty of the machine is, this is almost exactly the implementation. You want to spawn your workers using the spawn workers function, which basically says that you map the async which sort of asynchronously spawns your worker threads. And they were all trying to improve this MVX value. And Exodus was the list of strategies that we were putting into the thing. So really, and I think this is where you see the power of the program. We're just composing very simple parts together, and all of a sudden we have concurrent AI strategies all trying to get to the solution. And running this, basically how we dealt with exceptions. So what if one of the dwarfs suddenly died halfway through? Do we want the rest of the system to be effective? No. So this was a way of capturing, doing some error handling, but about the exception level, just in case. I don't think it was a good thing to do, just as a sort of safety feature. But nevertheless, there's still value in choosing the right dwarfs. We didn't want to just launch everything at every single instance. We wanted to just fine-tune things. And so we basically had a very simple heuristic whereby we would choose a certain subset of the dwarfs depending on the parameters of the mine. So if the mine was particularly small, so under a 7x7, we chose Sneeze and Loki. If it was a very large mine, we used Dock and Loki. Otherwise, we used some combination of the others. And this is where we did some fine-tuning, well, not so fine-tuning, but we tried our best to fine-tune this to be somewhat optimal. So was it really that simple? Well, it was not quite that simple, right? I mean, we managed to have this pure structure which we descended and did all the rest of it, but, well, of course, we had our own problems of our own, so preparation was a big problem. We didn't know which libraries to use to output text properly so that we could view the mines as they were going along. On the flip side, parsing was wonderful. We used Parsec, and that made the job pretty good, and it seemed fairly robust. But then the details of the simulator took us hours to fix because we were sleep deprived and things didn't work out quite how we wanted them to. A big problem was testing. We didn't really have time to set up a testing framework, and that would have been great because actually we shipped our solution with a critical bug, which meant that whenever what our robot tried to do was collect as many lambdas as it could, right? And so it would go chasing the higher order rocks, so it would make one fall on its head to get out the lambda and pick it up. But of course, rocks falling on your head will kill you. So that wasn't a very good strategy after all. But these kinds of bugs would have been nailed out if we had a bit more testing. And again, we didn't quite have time for this. Profiling, of course, that would have been nice to do. We never did any profiling. And visualizing, well, maybe visualizing some statistics about which branches we'd gone down, or just to see possible things. That would have been nice, but we just didn't have time for these kinds of things. So there you go, that's how we implemented our solution. I'd say that the experience was fairly good. We were happy with the way that we were able to modularize our program to be able to work as a team. We were working in two teams, one in Oxford, one in Utrecht, and communicating over Skype and whatnot. And actually working as these two cells meant that we had to make sure that we had a clean interface within which we could communicate to one another. And having that pure model for a mine was really essential because it meant that one team could be working on the parser, the other one could be working on the visualizer, and this mine thing kept absolutely stable. Of course, it meant going through this tree in a sort of generic way, in the sense that we didn't really care how you got from one end to the other, you were just exploring paths. It was wonderful, except of course that's what bit us when our simulator got things wrong. So, yeah, anyway, I think overall it was quite good. So thank you very much for listening.
So, questions?
Yeah. So I was trying very quickly to read your code and figure out if this is what was going on or not, but were the dwarves returning sort of incremental results, or did you just let them run out as far as they could, and each of them only touched the end part once?
No. So the dwarves produced an infinite, possibly infinite list of paths and scrolls, and the worker thread would go through that infinite list and check every single one of them.
Okay.
So it was sort of up to the dwarf to make sure that he was outputting good values, right?
Yes.
I mean, monotonically increasing would be fantastic.
Yes.
But well, we didn't rely on that.
Okay.
Good reason, I think.
Okay.
Yeah.
Any question? Yeah.
So, do you already know whether you won?
We certainly did not win. We made it through the first round despite this critical bug. We had another bug which meant that if the mine exit was on the northern, the most northern point, and we were underneath that. The program would segbolt. So this is kind of like a slightly idealized version of what was submitted. It's very close to the truth, I have to say that, but it's not exactly what we submitted. So no, that meant that we got through the first round miraculously. It didn't do too badly, I suppose. What were we, top 20 or something like that? Maybe not even there, I don't know. So, but we were completely eliminated in the next round, totally unsurprising.
You had 3 days time for that, but now the game is over, so you could spend some more time doing some profile visualization. Did you do that, or
I haven't done anything like that.
everybody stopped?
Yeah.
I was happy that it was over.
That's right.
Okay, thank you very much. So let's thank those people once again.